Hello and welcome to our video based entirely on sound waves. We've talked a lot about sound waves so far, but we haven't really focused on them, and so some of this is going to be review, but then some of it is just kind of diving deeper into some things that we've already talked about. Basics of sound waves. They are longitudinal. They're longitudinal waves, so they need a medium in order to propagate. And remember, propagate is just a very fancy word for move. They need a medium to even exist in the first place. There's no such thing as sound in space because there is nothing in space. There's no air, there's no gas that extends throughout all of space to make sure that the sound can actually move. The way sound works, let me see if I can pull this up again. Where was it? Aha, here we go. Yes. So this is what we looked at the other day. This is a really good interpretation of sound waves, okay, this animation. We looked at this in one of the other videos. And remember, it's a longitudinal wave because the air particles, that's the little black dots or red dots, move back and forth parallel to the direction the wave's moving. The wave is moving left to right in both cases. But the particles themselves don't actually end up displaced any farther than they started. They're oscillating. They're kind of moving around some central point. So the wave is made up of particles, but the wave is really the density, like that. There's different, it's like a density pattern, okay? So this, you know that this is a wave because a lot of the particles get kind of mushed together at first, and then that kind of pushes the wave along. It's a little trippy to look at. But the wave itself, it's made up of particles, but no particle stays in each wave for that long. It's just kind of pushing the density of the wave along. That's what a sound wave really looks like. Okay, and the reason that we get these sound waves is because of pressure variations. Pressure just means how many particles are in a certain area for our purposes. So the pressure variations, this is high air pressure, this is lower air pressure right now, high, low. And those variations just seem to move throughout the medium, throughout the air. Okay, so sound waves are caused by pressure variations in air. When you have air at a higher pressure, that's typically denser, and that's an area of what we would call condensation. Not condensation like rain, but condensation because it's condensed. Air at a lower pressure is less dense, and we refer to that as a rarefaction. Rarefied air comes from that. It means kind of thin air. So I'm going to draw basically the example that we just saw. It's going to take me a couple of minutes to do, but let's say here's an area of high density. Next to that is an area of lower density. Here's another area of high density. And then lower density again. High density. And lower density. And then finally high density again. The areas where it is less dense, these are rarefactions. In the areas where it's more dense, I'm going to draw over here. These are condensations. And remember, the reason that we have these patterns is because the air molecules are moving, they're vibrating, they're kind of knocking into one another, but they ultimately don't end up farther away from their initial position because of the wave. If they end up in a denser area, they're going to end up in a less dense area momentarily as the wave passes. But since the air particles are physically moving, since they're actually moving back and forth, there's actually some matter that is moving back and forth, we refer to this as a mechanical wave. Mechanical waves feature matter moving back and forth. Okay, so that's in general what a sound wave looks like. At STP, this is a chemistry reference, standard temperature and pressure. Okay. At standard temperature and pressure, sound waves travel with a speed of 331 meters per second. That comes right from the reference table, if they're traveling through air. Okay. Standard temperature and pressure is 0 degrees Celsius and atmospheric pressure. Atmospheric pressure is always true, but 0 degrees Celsius does not happen that often. Around here, it only happens at certain times of the year, from about April to November. Or excuse me, the other way around, November to April. If air is warmer, we can see from this graph right here that the speed of sound in air in meters per second goes up. At 0, if the air temperature is in degrees Celsius, if it's 0, then yeah, the speed is about 331. At room temperature, which is like 20 degrees, maybe a little bit warmer, it's closer to 344, 345. Okay? Matter of fact, I have a note written down here that the speed of sound at room temperature, which is about 20, maybe a little bit over 20 degrees Celsius, is approximately 346 meters per second. Now, why that happens, as you increase the temperature, the speed of sound keeps increasing. If you decrease the temperature, the speed of sound decreases. I think that probably has to do something with the energy, the kinetic energy that the air molecules have. Remember, warmer temperatures means more energy. The gases have more energy. Probably has something to do with that. The speed increases when the temperature increases. Okay? So in the winter, it's true that sound actually moves faster in your house than it does in outside, because the temperature would be colder. Now, that's sound as it relates to temperature. How does it relate to traveling to other materials? Speed of sound also increases typically for materials that are denser. So therefore, sound usually, and I say usually, travels faster in solids and liquids than it does in gases like air, such as steel and water. And if you look at this table, you can kind of see that relationship. There are, it kind of has to deal with the more dense the object, the faster sound will travel. That's not everything, but it's a good enough fit for us. So not a perfect relationship, but it's good enough for us. There are other factors, but we won't get into those. Okay? There's some quick basics about sound waves. Now, some more features. And again, we have talked about them, but it's important to really focus on them now. Why is that so blurry? Okay, there we go. Okay. The amplitude of a sound wave. So let's talk about those wave characteristics. The amplitude of a sound wave is related to its volume. The more energetic a sound wave, the higher the amplitude, and so the louder it will be. The frequency is related to the pitch, or other words for that would be note or tone, okay? How high-pitched something is. As you know, the relationship between sound waves' velocity, frequency, and wavelength is given by this equation, V equals F lambda. F is frequency, lambda is wavelength, V is speed. And here are the two facts that you need to know, and we haven't quite talked about these yet, but you're going to see, but they're related to V equals F lambda. Any sound wave in the same medium, so if you have multiple sound waves and they're all traveling through the same material, like the same temperature air, or they're all traveling through water, they all must have the same speed, okay? The material, the medium, is what determines wave speed. Therefore, if the speed is always going to be the same, the frequency and the wavelength are inversely related. The frequency and wavelength are inversely related. Okay? The frequency and wavelength are inversely related, meaning since the speed of a sound wave in a particular medium is always the same, the frequency, if the frequency goes up, the wavelength goes down. If the frequency goes down, the wavelength goes up, and vice versa. Okay? And that's important to remember. We're only saying for sound waves that are in the same medium. Obviously, if it's different mediums, sound waves will have different speeds, and we'll talk about that down here. So, an example. In air at STP, what is the frequency of a sound wave with a wavelength of 1.2 meters? Okay, how would we determine that? Well, since we know that V equals frequency times lambda, we would simply plug in 331 meters per second. We're looking for the frequency. We plug in the wavelength of 1.2 meters. We divide those two, and we end up with a frequency of 276 approximately hertz. There's our frequency. Okay, now, what if the wavelength is halved? What if another wave is produced that has a wavelength that is only half as big? Well, we know that it doesn't say anything about changing the medium or changing the material that the sound is traveling through. So, we must have the same speed. The wave must have the same speed. So, we do V equals F lambda again. It's going to be the same speed. So that means 331 meters per second equals the frequency times this shorter wavelength. If it gets halved, 1.2 divided by 2 is 0.6 meters. And since they're inversely related, you could predict that if the wavelength goes down, the frequency must go up. When I divide these two, 331 divided by 0.6, I get 552. Kind of makes sense. The frequency doubled when the wavelength was cut in half. That produces, if those two effects combine, to produce the same speed all over again. So 552. That's for sound waves that are in the same medium. Let's look at another example. What if sound waves travel from one medium to another? Obviously, their speed has to change. But if it's one sound wave that's already been created and it travels from one medium to the next, it keeps the same frequency. Okay? Think about it. The frequency has already been generated. That's how many times the wave cycles per second. Going to a different medium is not going to change that. So the frequency will stay the same, but the wavelength and the speed will change. So here's an example. In air at STP, a wave has a frequency of 480 hertz. Find the wavelength. Okay. V equals F lambda. In air at STP, that means the speed is 331 meters per second. We know the frequency is 480 hertz. We're looking for lambda. Therefore, lambda must be 331 divided by 480. We get about 0.69 meters. Nothing too troubling there. If the wave enters water, water has a speed, in water, sound has a speed of 1,496 meters per second. That's on the front. You can check me on that. What is the wavelength now? Okay. Well, we know that the frequency hasn't changed. The sound wave has already been created. The frequency can't change. The speed changed, and therefore, if the frequency doesn't change and the speed changed, the wavelength must change. The speed is now 1496 meters per second. The frequency is still 480 hertz. We solve for lambda, and we get 3.12 meters is what lambda is. Oops. Okay, so the speed of sound went up, the wavelength went up. And that kind of makes sense. If the frequency is going to remain the same, so imagine I'm drawing a wave here, if the frequency is going to remain the same, which means that the time that it takes for me to kind of draw these changes, let me start again. The amount of time it takes for one cycle, the period, doesn't change, so the number of cycles per second doesn't change, and the speed gets fast. The only way for that to happen is if the wavelength gets bigger, like this. Okay? So, sound waves that stay in the same medium, that are created in the same medium, all have the same speed. The frequency and wavelength are inversely related. If you take a single sound wave and bring it from one medium to another, the frequency stays the same, but the wavelength and speed may change. Okay, so we've got to identify, if we get a question like that, are we talking about one sound wave that's changing media, or are we talking about multiple sound waves in the same medium? The second and last thing we're going to talk about in this video is resonance. The definition of resonance, and we've kind of already talked about it, is one vibrating object that makes another object vibrate if the vibrations are at the second object's natural frequency. You take a vibrating object, an object that is vibrating, moving back and forth, you bring it near another object. The second object will start to vibrate if the frequency of the first object's vibrations are at the natural frequency of the second object. We actually see resonance all the time. And what I'm going to do is I'm going to list a whole bunch of examples of resonance. I'm going to show you one, but I'm going to list a whole bunch of examples here. And then in class, we're going to see most of those examples when I can demonstrate them for you in person. It's more effective if we do it that way. So the first one, I mean, you could do this one right at home right now probably. You probably have an empty water bottle somewhere. If you grab it and you blow across the top of it, you get a sound. So air blowing across the top of a water bottle. Okay? That creates a pitch. That's resonance. The air is causing vibrations that get kind of captured and amplified in the chamber of the water bottle. An even cooler demonstration is blow across the top of the water bottle, think about the pitch, take a long drink out of that water bottle, and try it again. You will actually get a lower pitch because you have changed the second object. You actually changed the natural frequency of the air column inside the water bottle because it's now longer. Okay, that's a really neat thing to do. I love doing that one in class. This one I will show you because this one you probably can't replicate on your own. 2 tuning forks. If they are identical, then one will vibrate because of the other. Okay? That means if one of the tuning forks is hit, then the other tuning fork will start vibrating even if it wasn't the one that was hit. I have a video for this. Okay, so this is a guy setting up 2 tuning forks. These boxes are not connected. Oh, that's really loud. Let me turn that down. Okay. He's going to hit, they're identical tuning forks. He's going to hit one with a little hammer. Produces a sound. Okay, we can tell the first one is vibrating. But look at that, he stopped the first one. And that second one is still vibrating. It only stops once he stops it. So what's happening there is the tuning forks are vibrating, and even though only the one on the right was hit, the one on the left started to vibrate because the one on the right has the same natural frequency as the one on the left. So it was vibrating at its natural frequency, and then therefore it started to make the second one vibrate. We know that they were both vibrating because he had to physically put his hand on both of them to stop them from vibrating. That's an example of resonance. One object vibrating because it experiences waves from another object that's vibrating. So tuning forks are a good example there. This one I can show in class. I was pretty excited when I figured out that I could do this. I am not a guitar player by any stretch of the imagination, but two guitar strings that are tuned to the same note will actually cause some resonance. One gets plucked, and the other vibrates. Okay? Two guitar strings tuned to the same note, one gets plucked. It doesn't even have to be one next to it. That's even really cool, so you know that the string isn't just like smacking into the other one. You pluck one, if the other one is at the same, has the same natural frequency, it will actually start to vibrate even though it hasn't been touched. A medical application of resonance is, hopefully none of you have ever had this or your parents, but a kidney stone, a lot of times what they do if it's a big one and they got to break it up, is they will shatter kidney stones with ultrasounds. Ultrasound is just an ultrasonic, basically they're sound waves. They actually put sound waves going through your kidney, and hopefully that causes the kidney stone to start to vibrate and to break up. Okay? Same principle actually is used in a lot of medical technology to map the inside of the body, such as like looking at like an unborn baby in a pregnant woman's womb. That uses ultrasound technology. Another example, if you're in band, you might have seen this before. If an instrument is just playing at just the right frequency, it will actually cause a drum to start rattling. You can hear this if you get like snare drums do this, I think. Let's see, what else? If we're heading towards summer, so during a thunderstorm in the summer, when there's a really big boom of thunder very, very close, what'll happen is the sound actually causing your windows to shake and or shatter or vibrate. This one we'll do in class, but I just like to call it the wine glass trick, where you take your finger and you rub it along the edge of the wine glass and it produces a sound. And then one you might not think of is a kid on a swing set. Okay? Little kids need to be pushed because they haven't figured out that they can actually pump themselves up to different heights. That if they move their legs at the same time, or at the right time, and pull with their arms at the correct time, they can actually start to swing up higher and higher without getting pushed by an adult. So a kid on a swing set, that's an example of resonance. Okay, you don't necessarily think of it as a wave, but they are basically, I don't really want to say causing a vibration to the swing set, but they are moving in such a way that they are amplifying their own motion. Okay, they're amplifying this periodic motion of swinging on a swing set, and that also counts as resonance. Okay, so the key here is that resonance happens all the time. Now, our last topic is beats. Beats in physics have a very distinct definition. The definition of beats is, let me move this up a little bit. The difference in frequency between two waves. That's a beat frequency. Okay, beat frequency simply means you got two waves. What's the difference in their frequencies? Now you can hear this, and this has great applications if you're a musician. Okay, you actually hear beat frequencies all the time at the beginning of band when you are tuning. I've got a little simulation here where I can play two different waves, 250 hertz. Let's say they're both at 250 hertz. I'm going to turn the sound on. Okay. So you should be able to hear the sound there. And it's a nice even sound. And this purple line is the combined effects. You can see that there's constructive interference happening. Well, watch what happens if I start to change the red wave. I'm going to change the frequency. I'm going to bring it up 1. Listen to the sound. All right. That's just obnoxious. It wasn't supposed to be that obnoxious. I'm sorry. So let's go back down to normal. Okay, 250. I'm going to bring it up 1. See how the sound kind of pulses in and out? How often is it pulsing? If you said 1 per second, you're exactly right. It is about at a frequency of 1 per second. I wonder why. Let's bring it up to 252. Seems like about 2 per second. As the difference in frequencies goes up, you start to hear more of this pulsing. Matter of fact, I can make it really annoying. There's a difference of 7, and it just sounds horrible, right? And actually, if you look at the purple line, you can see that there's some areas where there is constructive interference going on, right about at 0, but there's also some destructive interference going on. And look at this time scale, it's tiny, okay? There's 7 pulses here per second. Let's go back down. This is 3 pulses per second. Every time you hear a pulse, that's destructive interference, okay? How many times is there destructive interference per second with this example? About 3 per second. And look at that difference between the frequencies. What beat frequency means is it's the difference in frequency between 2 waves, and you hear it in how many little pulses you hear per second. So this is why some notes sound good together, some notes don't sound good together. It's because of the beat frequencies. And if you're tuning 2 different instruments, you'll know that they're out of tune if you hear that pulsing sound, okay? People who are in band will know exactly what I mean by that. Let's do one example because it does come up every once in a while. A trumpet that is already tuned to 440 hertz plays in conjunction with another untuned trumpet. When they play simultaneously at the same time, 3 beats per second are heard. What are the possible frequencies of the other trumpet? If you're hearing 3 beats, then the beat frequency is 3, which means the difference in frequencies between the 2 trumpets is 3. There are only 2 options: 437 hertz or 443 hertz. You'll have to experiment a little bit to figure out which one it actually is. If you tune so that the pitch goes up and there's more beats per second, then you know that it was at 443. We need to go back down. So there's a quick video on sound waves. Biggest things to take away here are that sound waves, well, all the basics, the speed of sound goes up in higher temperatures in air, goes up in denser materials. Sound waves in the same medium have the same speed. The frequency and wavelength are inversely related. However, if a sound wave travels from one medium to the next, the frequency stays the same, but the speed will change. We've got a lot of examples of resonance to look at, and beat frequencies, those are pretty easy. It's the difference in frequency between 2 waves, and we can hear that with the pulsing of the sound. I'm going to stop there. We're going to then, next, jump into light waves.